Auditorium. ITO. अरे तुम्ही इथून दोस्ते वाटतो आता बरे बॅग आहे कळलं का पुढे माईक केली two at the back and two at the front.
Good evening, friends, and welcome to this evening's public lecture. I request you all to please turn off your mobile phones. I'm often myself forget to do that. Okay, so we can get going. May I please request Professor Juan Maldacena, Mr. Narayan Murthy, our director, Professor Chenglur, and Professor Minwala to please come on the dais here, on the stage. So to start off this very special evening, I would like to request the director of TIFR, Professor Chenglur, to present a memento to Professor Juan Maldacena and Mr. Narayan Murthy on our behalf. So, friends, as you can see, we have two very eminent people as visitors with us today, and we look forward to hearing Professor Maldacena's lecture soon. Before that, Mr. Narayan Murthy, who has very kindly agreed to grace the occasion, has also agreed to make a few introductory remarks. But I am going to briefly introduce you before his remarks. Introduce him to you rather before these remarks. Of course, Mr. Murthy needs no introduction. He's a national icon, widely recognized as being one of the key people responsible for the growth of the Indian software industry, leading to India being the powerhouse in software that it is today. For his important, remarkable contributions, he has been given a number of awards, including the Padma Vibhushan, which, as you know, is one of the highest awards of our land. Mr. Murthy got his bachelor's degree from Mysore University, and I'm extremely proud to say that he got his master's degree from my alma mater, IIT Kanpur. In 1981, he co-founded the very well-known software company Infosys, and the rest, as you know, is history. Over the years, Mr. Murthy has emerged as a very powerful and important voice in the nation's discourse, emphasizing the importance of ethics, integrity, and hard work. He has also emphasized the importance of India striving for excellence in science and technology. He and his family, and I'm especially happy to welcome in our midst today also Mr. Rohan Murthy, his son, who is here with us. So the Murthy family is quite remarkable in both an understanding and concrete support that they have shown for the growth of scientific institutions in our country. And in particular, TIFR has benefited a great deal from their support and the support of Infosys over the years. And we just had a series of meetings in the afternoon acknowledging that in small part. In 2015, TIFR received an endowment from the Infosys Foundation for supporting research in string theory, so that we could redouble our efforts here along with our colleagues worldwide to try and unravel the mysteries of quantum gravity and understand the quantum structure of space-time itself. This endowment has proved truly transformative. And today, a decade later, we gather here today as a gesture, a small gesture of acknowledgement of that support and its help. And we are really grateful that Mr. Murthy agreed to be here with us in person today. Without further ado, please join me in welcoming him to the dais. I can move one of these.
I need one, that will be kept there. That's fine. Yeah, that's excellent. Thank you. Well, first of all, please accept my apology for increasing the average age of this August audience and reducing the average IQ of this August audience. It is always a privilege to come to this extraordinary institution. I will speak on a very important topic, which is very close to my heart, and that is, I'm very confident that Indian researchers will indeed solve our problems. In Israel, a land lacking in natural resources, we learn to appreciate our greatest national advantage, and that is the power of our minds. Through creativity and innovation, we transformed barren deserts into flourishing fields and pioneered new frontiers in science and technology. This was said by late Shimon Peres, the much respected leader of Israel. Such is the power of stunning ideas and high quality mind for every nation. A nation's progress on the economic and social fronts depends on the quality of scientific and technological research in the country. Research thrives in an environment of honor and respect for intellectuals, meritocracy, and the support and approbation these intellectuals receive from the society. Scientific research is about curiosity, daring, healthy skepticism, and questioning the status quo. It is following George Bernard Shaw's words, who said, "Most people see things as they are and wonder why. I dream of things that never are and then say, why not?" India is a land that once gave the world stunning ideas in mathematics and astronomy and surgery, perhaps. The plan to revive the power of science, technology, engineering, and mathematics, also called STEM, to solve the problems of our nation, started after we obtained independence 77 years ago in 1947. Naturally, this task has remained a very tough challenge. The Indian youth working in India have worked hard and smart to progress to the level of producing and using products for our own benefit from the inventions originating in the developed world. This is highly laudable, but sound, enduring, and quick scientific and technological progress requires us to go beyond just this capability and to invent stunning solutions to our unique problems. Global academic history tells us that good governance, academic freedom, meritocracy, encouragement, respect, admiration, and adequate financial support from the government and the society form vital engines for our getting back to the glory days of India in science, medicine, engineering, mathematics, and other areas to solve our great problems. What is a great problem? First, such a problem affects the life of a large number of people. Second, such a problem is a real world, concrete problem that we see around us every day and are unable to solve it. Third, the solution to such a problem is rooted in formal STEM theory so that the solution is verifiable, repeatable, and scalable. Let me substantiate my definition of a great problem with one example from my own field, computer science. I refer to the page ranking algorithm invented by Larry Page and Sergey Brin, two PhD students at Stanford University in 1990. It has brought revolutionary speed to web searching. Today, it is difficult to imagine a world without Google search. The commonality of the institution that engender such stunning ideas are one, an environment of total academic freedom, openness to new ideas, meritocracy, lack of fear of failure, adequate financial support, respect for the hierarchy of ideas rather than the hierarchy of titles, an environment of respect, admiration, and catalytic support from the government for academicians, and finally, most importantly, zero interference from bureaucrats and politicians in governance, management, and academic affairs of these higher educational and research institutions. I am pleased that our country has started creating such an environment so that our young researchers can indeed success in bringing fame to our nation. In addition, we must also start doing a few more things. First, there is enough wealth in India. Many of us spend large sums of money on charity, in education, and healthcare. We can contribute a part of this money to research to solve some of our national problems. Second, investment in R&D by the Indian industry is inadequate. For some reason, the Indian companies do not think of breakthrough in world-class products and creating inventive ideas as part of their strategy. I hope this too will happen in the course of time. Thank you very much.
So I will now introduce our speaker. Juan Martin Maldacena was born in Argentina in 1968. He was an undergraduate in Bariloche. He went on to do his PhD at Princeton University, then moved to a postdoctoral position at Rutgers, then was a professor at Harvard, and then took up the position that he holds now, namely a professorship at the Institute for Advanced Study at Princeton, the place where Einstein spent several of his last years. Okay. One is a string theorist. He's contributed tremendously to the study of gravity, quantum field theory, and their interrelationship between this remarkable ADS-CFT brought about by the remarkable ADS-CFT correspondence, of which he is the inventor. This correspondence that he discovered in 1997 is, in my opinion, the most important contribution to theoretical physics at least in the last 30, maybe 40 years. It's a remarkable breakthrough, and 30 years later, several of us are still trying to use it to understand various things. Okay, Juan's contributions have been recognized by several awards. I won't list all of them; it would take too long. But these awards include the Danny Heinemann Prize for Mathematical Physics, the MacArthur, quote-unquote, Genius Fellowship, the ICTP Dirac Medal, and he was one of the winners of the inaugural Breakthrough Award, actually, along with our very own Ashok Sen, who's also one of the winners of that inaugural award in 2012. Okay, so Juan, in my opinion, is a remarkable physicist on a historical scale, and it's our great pleasure and privilege to be able to interact with him and talk to him and learn from him. And today he will give us his public lecture. Thank you.
Well, thank you, Shiraz, for that very kind introduction. It's a real pleasure to be here. This morning I was reminded of the Physics Institute where I studied, which also sits near an army base, and I was hearing the noises in the morning of the army base. But well, regardless of that, it's wonderful to be here. I'm participating in a conference in this field of string theory, which is super lively and with lots of interesting ideas and questions. This is not my first time here. It's a second or third time here. It's a wonderful place, and I thank everyone who supports this place, including Mr. Murthy. And I was very heartened to see his vision for what research in society and its role in society. And I think India has a very bright future. Okay, so today I wasn't intended to. Let's see. Let's first get the slide advancer to work. Okay. It's not yet working anyway, so I can. Anyway, so Galileo said that well, the topic of the talk will be space-time and our modern ideas of space-time. And before we start, I should say that, well, this is the title, Black Hole, Wormholes, and Quantum Entanglement. We'll try to go through these ideas and explain what they mean. Before we start, I would like to remind you of this idea that Galileo had, that the book of nature is written in the language of mathematics and geometry. And we'll try to see what this means through various examples. Eventually, I'll learn how to use this. Yeah. So let's talk a bit about geometry. So you all are familiar with the concept of Euclidean geometry that involves points, lines, circles, etc., and their relationships. I probably don't need to explain this too much. We use it for many things. In particular, for example, we use it to describe images. All the images in your computers are generated by these very basic ideas of geometry. And this idea of geometry historically got some big development from the technological necessities of the time, such as measuring fields and levying taxes and so on. And the Greeks formalized and abstracted the rules of geometry, and they had a series of axioms from which they could deduce various theorems in geometry. And I'm not going to list all the axioms. I'm just going to give you one, just to give you a flavor of what the axioms look like. So one of the axioms is that if you have two distinct points, then such as this point and that point, then there is a unique line passing through them. And then there were some other axioms that I'm not going to list. Now, this process of formalizing geometry has continued to this day. And we now can imagine curved geometries, higher dimensional geometries, all kinds of geometries. And so geometry is a very basic notion that we encounter in many places. Sometimes it's possible to find it in some unexpected places. And so let me give you an example that involves a children's game. So this is a children's game called Spotted. I don't know if you know it. It's some card game. And the objective of this game is two players. By the way, I'm not getting any ad money. And the objective, so people, so there are players and they put the cards. And the objective is, given two cards, is to find the image they have in common. So for example, this card and that card have that little bomb in common. And for example, these two cards have this image in common and so on. And I let you try to find the image in common between, let's say, these two cards. So they all have some image in common, and the one who finds it first wins the game. Now, what's the geometry behind this? So one property of these cards and their images is that given any two different cards, there is a unique image they have in common. So for any two cards, you can find an image they have in common. And this will remind you of this axiom we discussed in geometry, that saying that two different points, there is a unique line in common. So there is a sense in which each card is like a point in some geometry, and each image is a certain line. And in fact, the arrangements of figures and images in these cards follows some principles of finite geometry that was developed in the 17th and 18th century, which have this axiom in common with Euclidean geometry, but some other axioms are different. But here you get the idea, and if you want to count how many possible cards you can have with a certain number of images and so on, you have to rely on, or you can rely on this geometry. Now, there is also a higher dimensional geometry behind the language models, such as ChatGPT, where words are represented at points in a higher dimensional space, with spaces with dimensions that are very big, like 12,000 dimensional space. Now, so geometry can be used for many things. Historically, one interesting application was determining the shape of the Earth. This is what Eratosthenes did. And he noticed that if you have a stick, a vertical stick at the equator, then the shadow, there will be cast no shadow. But if you're not at the equator, then it would cast some shadow. And by measuring this, the angle made by the shadow and the distance between these 2 points, he could figure out the size, the radius of the Earth, and determine the size of the Earth. This is a famous thing that you probably all heard about. So one thing we learned is that actually Euclidean geometry is actually wrong for determining the shape of fields and the properties of fields, because the surface of the Earth is not flat, but is curved. And of course, this doesn't matter if your field is small, but it will start mattering if your field is very big, so that, let's say, for example, the sum of the angles of this triangle does not add to 180 degrees, as it's supposed to do for flat Euclidean geometry. So we have Euclidean geometry, which is good if your fields are not very big, but if your fields are very big, then we have to rely on the curve geometry of the surface of the Earth. So this is a first example of going between a flat geometry and a curved geometry. Now let's go back to physics. So this was all geometry. And let's recall an important principle that was discovered in the beginning of the 20th century. So the principle of special relativity, which says that observers moving with constant relative velocity obey the same laws of physics. Now, actually, this principle was enunciated by Galileo several hundred years ago. But the new aspect is that one of the laws of physics is that the speed of light is the maximal speed of propagation of signals, and that this velocity is the same for both observers. So this is highly non-obvious. So what this is saying is that if you have two observers, one is stationary and the other one is moving, and they are both observing this light, one would be tempted to say that this one will see it moving more slowly, but in fact, both see it moving exactly at the same speed. And the trick that makes this work is that time flows a little more slowly for this observer. So that's one of the consequences. But these ideas of special relativity suggest that one should think of space and time. One can put them together into a new kind of geometry. Again, making now geometry out of space and time. And this is geometry in which points are events. Recall in geometry, we are free to define points to be whatever we want, as long as they have some proper relationships. And so points are going to be events, so things that happen at some position and at some time. So the beginning of this talk was one such event. And lines are trajectories of particles. So for example, if we think of this horizontal direction of space and the vertical direction of time, let's say we are standing here, there was the beginning of the talk, now there is, let's say, the present time of the talk, and then it will continue to the future. Now there are maybe other events, some event over there, and we could have lines. So if we have a particle that moves with some velocity relative to us, it will be describing this trajectory, and so on. And then there is a line with maximal velocity, that's the speed of light. And there cannot be a line that with more, there couldn't be a trajectory of a particle that moves with an even higher velocity. Okay. And we can represent that, that geometry, the geometry of space-time, in this case, in this two-dimensional space. That now here we divided time and space along these directions, and this division is somehow works for this observer who goes just straight up. But if we were following, for example, this other observer would divide space and time in a different way. So we would perhaps for this observer, space would be this direction and time would be along his trajectory. Okay, but the main conclusion that I would like to draw is simply that we can make a geometry out of space and time. And so now we will make a small detour, a small apparent detour from geometry. Okay, so we'll start discussing the force of gravity. Of course, the study of the force of gravity goes back, let's say, to Newtonian gravity. And so Newton said that if you have a very big mass and you have some, let's say, little small mass, then the acceleration of this little small mass will be proportional to some constant called the Newton constant, which says how big the strength, how strong gravity is, and it's proportional to 1 over r squared. So some specific formula that tells us how the force of gravity works. Now, for our continuing story, there are two important points. One is that the acceleration of this small mass is independent of this small mass. Okay. So, and the second feature is that it's an instantaneous force. So the direction of this force, for example, depends on this distance. And if we were to vary the position of this mass, the force would instantaneously change. So those are two features. Now this looks a problem for relativity because it might seem that by measuring the force here, we can determine the position of this mass. And this is a problem for relativity. But this first point is saying in particular that all objects fall in the same way in a gravitational field. And this led Einstein to what he called his happy thought, which was the realization that if you fall freely in a gravitational field, your weight disappears. So the main effect of gravity disappears. So he imagined someone who was, let's say, in an elevator. Imagine someone standing on a scale. So if the elevator is just standing still, the scale would mark its weight. But imagine now that someone cuts the ropes of this elevator, the elevator starts falling freely. Then the person would feel that he's floating, and the scale would mark 0 weight. Okay, the weight would have disappeared completely. It would be a problem when the elevator hits the floor, but we won't worry about that. So, of course, an astronaut that is in space, orbiting the Earth, is in some sense falling in the gravitational field, or being moved by the gravitational field. But both the spaceship and the astronaut are moved in exactly the same way, so it looks as if they were floating. Okay. Now, this idea then led Einstein to develop the theory of general relativity. This is Einstein's theory of gravity, and is based on the idea that the geometry of space-time is not flat, but it is curved by the presence of matter, and that particles move along the space-time along the, let's say, shortest trajectory. So the shortest line is not let's say, a straight line that we were drawing before, lines of constant velocity, but could be lines where the velocity is changing, but it's changing in such a way that a particle is constantly trying to find the, let's say, shortest, in some sense, trajectory. More precisely, is the trajectory where the experience time of the particle is as long as possible. So in particular, also matter curves space-time, so that curvature of the space-time is produced by the presence of matter. And then there are some equations that roughly say that the curvature is proportional to the matter density. So again, space-time is a curved geometry. Points, again, are events. And the straight lines in this curved geometry are the trajectories of observers falling freely. So, and for our everyday experience, of course, we're pretty close to flat space. So the effects of curvature are small, but we do feel some of these effects through our weight, for example. But we can find that space-time is curved, and let's say an interesting demonstration is the fact that if you have galaxies far away and you have some other galaxies or mass distribution a bit closer, then this can bend the direction of the light rays, and it could be that two light rays which initially are diverging then converge back onto the Earth to the same point. This would not be possible in flat space. So in flat space, if two lines are going away from each other, they never go back and converge. And so in this sense, these galaxies here are acting as a kind of lens, and this is sometimes called gravitational lensing. But it shows, it's a drastic demonstration that space-time is curved, and this is one image, astronomical image, where this is some group of galaxies, and they are bending the image of some faraway galaxy, in this case, the blue one. So light rays show us that space-time is curved in the same way that Eratosthenes discovered that the Earth was curved. So we're again using light to probe the geometry of our world. Eratosthenes was just the surface of the Earth. Here is just the structure of space-time. Now, this theory had one very interesting prediction, which was the idea that there are gravity waves. And the reason there are gravity waves is related to the fact that the force of gravity is not instantaneous. So if you start moving a mass, the other mass cannot detect that immediately. That information has to travel at some speed, and its travel, this shaking, let's say, of the masses, produces a distortion in the shape of space-time that travels at the speed of light. And these waves were first detected in 2019, and this is a very active area now of research to detect these waves experimentally, and they're telling us very interesting things about the universe, which I won't get into. Now then, general relativity also had two very surprising predictions, and one was black holes, and the second was the expansion of the universe. And these were very surprising because Einstein himself was so surprised that he doubted these predictions. In fact, I love this phrase I often mention. So Einstein told Lemaitre was the one who was discussing the expansion of the universe. He said, "Your math is great, but your physics is dismal." And yeah, that's sometimes what other physicists tell us string theorists. No. And we hope that we are as right as Lemaitre was. So, now, we now have great observational evidence for both of them, both for black holes and for the expansion of the universe. So this is a very beautiful picture from the Event Horizon Telescope. That's a picture of the gas surrounding the black hole at the center of the Milky Way, our own galaxy. Has a supermassive black hole in its center, and this is a great piece of evidence for the existence of this black hole. We have a lot of evidence of the expanding universe from the cosmic microwave background and many properties of galaxies and so on. Now, after this discussion of general relativity, so we discussed geometry, we discussed how geometry was very important for general relativity, and now we'll get into a new topic. We'll introduce a new topic, and that's the topic of quantum mechanics. So that's one of the two great revolutions in the early 20th century. Classical physics was extended, well, we extended it by the discovery of special relativity and then general relativity. And then also quantum mechanics was discovered more or less at the same time. Now, what is quantum mechanics? I won't discuss it in great detail. So it's a new type of description of physical systems that is intrinsically probabilistic. So there is some intrinsic probabilistic aspect to the motion, or if you wish, the behavior of physical systems. And in particular, it has one feature which is called the uncertainty principle, which is that there are some things which you cannot know at the same time. So you might know the position of a particle, but not its velocity, or vice versa. And quantum mechanics has great explanatory power. So it explains chemistry, it explains atoms, etc. So all of the properties of matter that we know and love are determined by quantum mechanics. But it's really a weird explanation. It's an explanation where, you know, atoms are mostly empty space. And it requires a lot of work to explain simple, obvious things, like, you know, why light gets reflected from a surface, or why is matter, you know, solid, and things like this. In fact, the physical appearance of most substances are emergent properties. What this means is that they arise from having a large number of quantum particles and their interactions. So we can't really say what's, let's say, the color of an atom of copper. But if we have, you know, lots of atoms of copper, then we can say it has the familiar reddish color. Now, when even the appearance of matter being solid, so for example, here someone is standing on the surface of the rock, so that's very solid. Here we have an insect standing on water, and we say, well, that's maybe the insect is very light, that's why he can stand on the surface of the water, but water is not really solid. But really, in both cases, matter consists mostly of empty space. So if instead of being a person, you were a neutrino or a dark matter particle, or if you were made of dark matter particles, you could just go through matter with no problem. So we'd be going like empty space. Any of these particles can go through the whole Earth without scattering against anything. So it's very hard to get them to scatter against anything. So, yeah. So now we'll have to talk about yet some other concept, which is the joining special relativity with quantum mechanics. And this is something that was developed from the 30s and, let's say, until the 70s, something called quantum field theory. I mean, the research in quantum field theory, of course, continues to this day. And this is the kind of theory we used to describe particles moving at very high speeds, like in particle colliders and so on. And this describes the interactions between elementary particles, and it's the kind of theory we use to describe the fundamental forces of nature. For example, one of the things this theory says is that there is some quantum of light, which is the photon, and we can think of the forces as exchange in these particles. Now, we said we use geometry to describe pictures. We also use these pictures, these lines in space-time, to describe the interaction between particles. There is some sense in which there is some geometry behind these lines. Actually, these lines represent some mathematical equations, and there's lots of geometry people continue to uncover to this day about this description. And we use that to describe, we use those diagrams to calculate what happens in particle collisions. That's a picture of, well. So in this way, we can describe all of the matter we see. And an important question is how do we join quantum mechanics with gravity? So how do we go from something like quantum field theory to something we can call quantum gravity, so quantum mechanics of space-time. And nature, we know general relativity describes many aspects of nature, and that quantum mechanics describes many aspects of nature. Nature is really one thing. It should be consistent with both principles, and so there should be a theory that describes both aspects of nature. Now there are, let's say, two approaches to quantum gravity. One is some approximate approach, which is similar to quantum field theory. So gravity is a kind of field theory, and we can quantize it by using similar methods that we use to quantum field theory. And that works and gives some approximate answers to many things. But it has a problem giving precise answers. It has problems under certain circumstances. When the space-time curvature is very large, then we cannot apply this first approach. And then we need a more precise approach or a full theory of quantum gravity. Now, the approximate approach is roughly saying that we describe the gravitational force by adding a new particle, which we call a graviton, and then we think about the same type of diagrams or geometry that we were discussing previously. And this works pretty nicely when the radius of curvature of your universe is much bigger than a very short distance called the Planck scale. So the Planck scale is some combination of G Newton, H bar, and C that Planck made. So you can make this combination, and Planck realized that when he discovered quantum mechanics, he realized that when you go to very short distances, the force of gravity should have a drastic modification at this short distance scale. But if your distance is much bigger than this scale, there shouldn't be any drastic modification. So this is a theoretically calculated distance, and it's very, very tiny, 10 to the minus 35 meters. It's so tiny that I should remind you what the smallest distance we can see today is 10 to the minus 18 meters. So this is the smallest distance we can explore today using the Large Hadron Collider. That's the biggest microscope we have. And this is much, much smaller, right? So this is a distance, this is theoretically predicted distance at which the effects of quantum gravity should become of order 1. They should become very important. At longer distances, they are smaller. And for this reason, this simple sort of field theory approximation to gravity will be correct for most circumstances in our everyday life, okay? Not only in our everyday life, but also in most places in our universe, this approximation would be correct. Now, there are some circumstances when the approximate approach fails. For example, the most important one is the singularity at the beginning of the Big Bang. And also there is a similar singularity in the interior of the black holes. Now, what does the word singularity mean? The word singularity means that the curvature of space-time becomes infinite in some region. So becoming infinite means that the equations of Einstein's equations cease to be valid. They give nonsense, okay? So Einstein's equations themselves predict that they should fail. They should fail in certain circumstances. And for that, we think that when this happens, there should be some quantum corrections that will fix that. and will give us some reasonable answers. The most interesting failure is at the beginning of the Big Bang. So we don't know what happened in the very beginning precisely for this reason. So we can extrapolate the laws of physics backwards in time when the universe was smaller and smaller and smaller. I mean, recall the universe is expanding. So when you go back in time, it was smaller and smaller and smaller. And when it gets to be smaller than this Planck distance we were talking about, then we don't know what happened. And so in order to know what happened at that point, we need a better theory, the theory of quantum gravity. So we'll come to the full theory later, but we'll first discuss some important successes of the approximate approach, the first approach I mentioned. And it actually, this first approach led to a big surprise for black holes. And that's the idea that black holes emit Hawking radiation. And that was discovered by Hawking. And he discovered the formula for the temperature that says that the temperature of the black hole increases as the black hole size decreases. So if you have a very big black hole, it will look kind of black. If you have a smaller one, it might look a little redder. And if you have sufficiently small black hole, it would look white, okay? And that's what's surprising about this effect. We have the oxymoron of a white black hole, okay? Now, the temperatures for black holes that are astronomical, the type of black holes that are produced by collapse of stars, is super, super tiny. So this is an effect that is too small to be detected for astrophysical black holes. However, if you had a black hole that you somehow managed to make, it would be difficult to make. But a black hole that has the size of a bacterium, that's roughly the size of the wavelength of visible light. If it has such a black hole, it will look white. So if you look at it with your eyes, it will just look like a little tiny white dot. So it will be a black hole which is not black. So that's a surprising thing. Now, where did this phenomenon of Hawking radiation come from? So we'll try to give you I'll try to give you a qualitative explanation. So the reason is that the quantum vacuum, the vacuum in this theory of quantum field theory, is a complicated thing basically because of it's related to the uncertainty principle. So if you look at the small region of space-time, that small region will not be in a fixed state, it will be in a fluctuating state. And if on the other hand, if you have a big region of space-time, then it will be in what we call a single quantum state, some definite state. And what happens is that the fluctuations you see in one region are correlated with the fluctuations that you see in a different region. Now, those correlations are special kind of quantum correlation that we call entanglement. I want to explain in detail what's entanglement, just for the purposes of this talk, is some type of correlation. Now, let's describe this with an analogy. Let's try to get to this concept of correlations between different regions of space with a simple analogy. Imagine someone tells you the portion of a sentence. So, for example, Mary stepped out of her, okay? This is a portion of a sentence. We don't know how the sentence continues, right? So it's a sentence that doesn't quite make sense. Makes a little bit of sense, but the full meaning is not clear. We know it involves Mary. We don't know the full meaning. It could end in different ways. But if someone told you the full sentence, let's say Mary stepped out of her comfort zone by explaining quantum physics to a group of investors, then you get the full meaning, and it's one of the ways in which the sentence can end. There are many other ways. Then you get the well-formed sentence with some meaning. But if you only have a portion of the sentence, you lack some information. You get the full sentence, everything is well correlated, a full concrete meaning. Now, we can quantify the information we lack by listing the various ways we can complete it. And ignorance is quantified by something called informational entropy. Some idea of information theory is also related to the entropy we use in thermodynamics. Now the full vacuum is like a well-formed sentence. So everything is, has some meaning. And a small region is like a part of a sentence that is kind of a bit random. Now let's return back to black holes. Now, the geometry of a black hole is a curious thing where it is divided. It contains this singularity we mentioned, a region where the space-time curvature becomes large. This is a diagram similar to the diagrams we were drawing before. Time goes vertical, and we're imagining just only one dimension of space. I'm suppressing two of the dimensions of space. Lines here, light-like lines, move up 45 degrees. This is the trajectory of some imaginary light line that divides the space in two regions. So in the region inside, if you are inside and you try to go out, you end up here at the singularity. While if you are here, you can go out and you can go out and you never fall into the singularity. Unless you, of course, you decide to move left, but you have the option of moving right and escaping the singularity. So this line separates what you can see from the outside from what you cannot see from the outside. So nothing here can send a signal, no point here can send a signal to something which is outside, because that would require moving faster than the speed of light. Now, if we have the vacuum state, the vacuum is somehow divided into two parts by this line. And if you are outside, you only see, divided in the sense that if you're outside, you only get to see this part of the vacuum, okay? Only a portion of the vacuum, not the part that is inside. So the vacuum is a bit like a sentence that we only see part of the sentence, half of the sentence and not the other half. And for that reason, it looks a bit random. And that randomness is related to, you said entropy, temperature, thermal aspects, all those things are related. And that's basically the origin of Hawking radiation. Okay. Now, for a black hole, we can calculate this entropy using the laws of thermodynamics. They give us a way to calculate it. And the net answer is that this entropy or disorder is the area of related to the area of the black hole in some units which are the same length units we discussed before when the quantum effects of gravity were becoming important. This is because it's a gravitational effect. And it's a huge entropy for a macroscopic black hole because this LP is very, very tiny. So it's much bigger than the entropy of any physical system of that size. Okay, so this is the entropy associated to black holes. And there's also a second law of thermodynamics, which is related to the fact that the area always increases. And this is a consequence of Einstein's equations. There is some intimate connection between Einstein's equations and thermodynamics. A bit surprising because Einstein's equations naively are classical. It's surprising that they have any relation at all with the laws of thermodynamics. Now, black holes with emit radiation, they will lose mass and evaporate. And these effects are, as I said, are relevant for astrophysical black holes. However, if you had a small black hole, let's say a black hole of a mass of 1 kilogram, it would be very hard to make, but if you could make it, then it would evaporate almost instantaneously and making an explosion which is worse than a 20 megaton nuclear bomb, the largest nuclear bomb. Fortunately, there are no such black holes around. Now, we discussed some results for black holes that follow from the approximate method, but there are some questions we cannot answer using the approximate method. So, for example, we can form a black hole and something comes out. How do we recover the information of what went into the black hole? That's something we cannot recover from the approximate method. And the question is also whether this process of black hole formation and evaporation or disappearance is also consistent with quantum mechanics. That we can't answer either. For that, we need the full theory of quantum gravity. Now, we don't have a full theory of quantum gravity. We have something we could call a theory under construction, which is the so-called string theory. And maybe one way to represent this is that we see that there might be something. The string theory is what is behind this fog, okay, that we don't understand completely. Now, so this is the string theory we know today. But in this talk, I'll try to explain it without using mathematics, so it will be even less clear. And okay, so let me try. So one of the things that we learned through string theory is we're learning some interesting properties of black holes. And today we're focused on just one aspect of the theory, this idea that space-time can be an emergent concept, similar to the surface of the water that we discussed or the solid aspect of materials. So now in this analogy, so water is to atoms as space-time is to what? So what are the analog of atoms? Are there space-time atoms? What are the space-time atoms? Fundamental units of space-time. The idea is that there is something like that, but those atoms, or maybe we should call them qubits, the fundamental quantum degrees of freedom of space-time, are somehow far away. They are not where you thought they might be. And this concept is called holography, which says that you can describe the physics of gravitational spacetimes in terms of what's going on far away. This works particularly well in negatively curved spaces. This is a picture of a negatively curved space. Escher made these very nice pictures. And so the idea is that gravitational physics here reduces to a theory of ordinary quantum mechanics or ordinary quantum field theory at this boundary. This is a conjecture with some evidence, and there is more evidence that it is correct, and we are still understanding various aspects of it. So this is maybe one way to say what's going on. So we have gravity in the interior. We might have a particle that is moving in the interior. In the boundary, this is represented by a bunch of other particles that are moving and interact. So this random motion is trying to represent the fact that these particles are interacting strongly with each other. Now we can ask how we describe a black hole. And the idea is that the black hole would be described by a fluid of particles far away. So this is some fluid at finite temperature. And the temperature and entropy of the black hole, that big entropy we discussed, comes from the entropy of the particles far away. By entropy, it means that these particles at the boundary can be many possible states or many possible configurations. And summing over all of them, we get some big number of configurations. That's the entropy. Now, the theory on the boundary obeys the rules of quantum mechanics, and therefore so does the black hole in the interior. And so this would be telling us that black holes are consistent with quantum mechanics if you accept this holographic conjecture. Now, I should say that I mentioned that the particles at the boundary are some kind of fluid of particles that are moving in some intricate ways. And this correspondence between black holes and fluids was studied in great detail here by the TIFR group, such as Shiraz Mingwal and collaborators. They made great progress in this. And they discovered that certain fluids can have certain anomalous properties. They behave in some strange ways, something they discovered using gravity. But then after you discover it using gravity, you find that this idea also has some problems in condensed matter physics and nuclear physics that have nothing to do with gravity. So it's a general property of fluids that they can have these particular patterns. So this is an example where they use black holes to discover patterns that are present more generally. In some interesting way, black holes became a source of information. Now, let's emphasize one aspect of holography. And this is the idea of emergent geometry. So the idea is that we have qubits that live here, far away in this negatively curved space. But then we have this extra dimension that is the space where gravity lives. So it has one extra dimension. So let's try to explain this with an analogy. So the analogy is the following. So imagine a sentence again. So this particular sentence, if a man does not keep a pace with his companions, perhaps it is because he hears a different drummer. Okay. Now, when you hear this phrase in your mind, you analyze the phrase, you divide it into the various words, and you group the words, you parse the sentence, you group it into groups of words. And so there are these various layers of analysis that you've done in your mind almost automatically. If you built a computer program, this computer program would have to do this analysis. You have to make sure that it does that. And you can find the various subphrases and so on. And you can even discover some long-range correlations between certain words. For example, the word man, his, and he are all related, right? The word keep pace is related to drummer, perhaps in a deeper way. So, and in this way, once you made these whole layers of analysis, there is a more superficial level of analysis at the level of words and some deeper level of analysis that depends on the correlations on all the words together. Doesn't depend on a single word, but all the words together. Okay, so the analogy is that the idea is that here, the state of the quantum system is like a very long sentence that is up here. And the space-time is a kind of analysis that analyzes this sentence and tells us about the correlations present among the words in this sentence. And particles moving in the space-time can represent perhaps some long-distance correlations between specific words that you have in this sentence. Now, we could say that a bulk observer, so someone who lives here in the interior of space-time, is a bit like a character in a novel whose text is written at the boundary. Okay. Now, what is a black hole in the space-time? So let's go back to the sentence. Maybe I'll just stand here because my clicker doesn't work very well. So we'll get back to the sentence that we had before, and now we'll change some words. So here we change the word eats, she, and lectures. And the sentence makes sense up to a certain level of analysis, but we lost the full meaning of the sentence that it had before. So there is some kind of horizon of meaning. The phrase, the sentence ceases to mean something at some level of analysis. Now we can make more changes, and if we make more changes, then it makes even less sense. So in some sense, the horizon grows, the amount of ignorance that we have grows. If we change all the letters to random letters, then the horizon grows as much as possible, and the area is related to the entropy or to the ignorance that we have in the sentence, the amount of errors, if you wish, or noise that we put in the sentence. Now, the idea that the entropy increases or that the area should grow is related to the idea that if you just take a sentence that is a well-formed sentence and you start making changes at random, you're more likely to mess up the sentence than to make a new, nice, good sentence. So, now, imagine that these changes that we made here came from a reversible process. For example, an encryption algorithm, the type of algorithms your computers use to communicate safely through the internet. If that happens, then if you know the encryption key, you can run it backwards and then recover the information. So you can reverse that process and recover the original sentence. Okay. Now the laws of physics at the boundary change the state of the boundary, so that's like a change in this sentence, but they're analogous to an encryption process in the sense that it is reversible. So lots of physics are reversible, and so any type of entropy increase or anything like that you might experience just arises apparently because you don't know perhaps the encryption key or you don't know the precise laws of physics. But in principle, we can undo the formation of the black hole and recover the original information, right? So we can undo the laws of physics, we can evolve the system backwards and recover the original information. And that's how, in principle, you could recover the information from a black hole. Now, the lesson from this is that, the lessons you should draw, perhaps, is that space-time emerges from quantum entanglement, which is it's a form of correlations between the degrees of freedom at this boundary, and a type of quantum, entanglement is a type of quantum correlation. And geometry, the space-time geometry represents some patterns in this entanglement, in these correlations, or geometry summarizing these patterns of correlations. And it's somewhat similar to how meaning emerges from a sentence from the correlations between the different words that we have in the sentence. Now, this type of picture we drew for the sentence is similar to the types of pictures people draw to represent a quantum entanglement in certain physical systems. This is taken from a picture from some papers that discuss patterns of entanglement. And so the correspondence actually is somewhat close between the two. The only difference is that in the case of the sentence, the correlations are just classical. In the case of, in this case we're talking about, these are quantum correlations. Actually, in fact, here at the TIFR, this connection between quantum information and spacetime is actively studied by Onkar Parikar and Abhijit Gade and many collaborators in the group, and they're making very interesting progress. Now, that's the end of this analogy for now. And now we'll discuss some extreme case of the relationship between entanglement and geometry. So it will be a funny feature of it. So first, before we discuss it, we'll discuss a particular space-time geometry. And it goes back to the space-time geometry of the black hole solution. So that's the first solution that Schwarzschild found many years ago. When you analyze it very carefully, that simplest solution turns out to have an interesting surprise. And that is that it doesn't describe one black hole, but it actually describes two black holes. So let me first explain how that works. So imagine, so the idea is that that solution describes a configuration that is very close to the following. So it's close to a situation where you have two black holes that are very far away from each other, but sharing a single interior. So they are somehow connected through the interior. Let me draw some pictures. So it's roughly as if the structure of this space was such that they are somehow connected through the interior. Now, this connection is between the two is time dependent. So as time goes, so at one instant in time, we have this connection. So at one instant in time, we have some connection between the two sides. But as time progresses, this connection gets thinner and the distance becomes larger. And in such a way that if you are an observer that starts on one of the sides, you cannot emerge on the other. So even though they share an interior, you cannot send information through this type of, let's call it wormhole. So that's that's what the solution looks like, and it's the simplest GR solution of a black hole. And the interpretation is that the idea is that there are some qubits that describe this black hole that are in some random state with some entropy. And there are the qubits that describe this other black hole, which also has some entropy, but they actually entangle with each other in such a way that the combined state itself has no entropy. And they're correlated in some very special state. And that pattern of correlations implies that or is connected to the fact that the black holes, the interiors are connected. So the connection between the two black holes comes from the entanglement of their degrees of freedom. So let's describe this with an analogy for these correlations. So let's go back to the sentence. So here we have, again, let's say a sentence, the same sentence we had before. And here we have the same sentence, but in a different language. In this case, I chose Spanish. Now, when you analyze this sentence, the particular words are different in the two sides, right? But when you get to a certain level of analysis, they will have something in common. The meaning is actually common for both sentences. So as we try to look for the correlations, it reaches a point when the two are the same. So they are somehow connected. That somehow is similar to this phenomenon we have of the interior of black holes being connected. Now, there is another twist of this relationship, of this connection between the different black holes, which is that before we said the two black holes were very far away and not interacting. But if you bring these black holes a little closer and they start interacting with each other, there is a new interesting phenomenon that happens, which is that this wormhole, this connection that we have between the two interiors, now you can start being able to send signals through them, through this connection. these signals are not a shortcut. So this is not a shortcut in space-time, so it takes longer to go through this wormhole than it takes to go through the outside. But the interesting fact is that this connection, which was before was hard to see and so on, now becomes something more concrete, where you can send signals you can send signals through the wormhole. And in fact, this type of mechanism for sending signals through entangled states is sometimes called, well, it's called usually quantum teleportation. And when we have this emergent spacetime, as we are discussing, this teleportation can happen through this wormhole. Now, let's talk about an analogy for quantum teleportation through a wormhole. So we have three elements in this discussion. So one is entanglement. There is communication, which has to do with the interaction between the two black holes. And then there is some kind of wormhole. So let's imagine that we have Alice and Bob, and they've been married for many years. And for this reason, they share many memories, many common memories. And then Alice gives Bob a look, okay? And Bob immediately knows what he should do, okay? So through this process, there was some set of ideas that Alice had, and there is also a set of ideas that Bob has. And the look, for someone who looks from the outside, conveys no information. Because someone from outside does not have access to the ideas that either of them has. But because of the correlations that are between those ideas, this look is transferring some information. It's transferring an idea from Alice's mind to Bob's mind. Okay. So now we've been discussing this wormhole in the simple context of this original Schwarzschild solution. But there are similar wormholes that are important for understanding how information is encoded in Hawking radiation and how information comes out of black holes. And there was very interesting progress on this by these authors. Actually, Ahmed Almeri is one of the participants here in the workshop. I don't know if he's sitting here somewhere, but he's currently visiting also the IFR. And they've been used to solve some long-standing problems about black holes and information and how black holes process information. So the conclusions are that quantum systems give rise to some geometry through correlations, and that geometry could look very similar to the geometry of our own spacetime. So it could be that at least this is what happens in models that we understand in some detail, and it could be that our spacetime geometry might be emergent in a similar way. Now, there is an interesting consequence of this, which is that we could make artificial tiny little universes in the laboratory by creating quantum systems that have this the type of correlations that are necessary to create some spacetime. So we could make by tiny little universes some emergent geometry that's governed by Einstein's equations. You would need to have the smallest universe that you could do with that is approximately governed by Einstein's equations. You can estimate that you would need to have around 10,000 qubits. Of course, in contrast, our big universe would need 10 to the 120 qubits. So there is no hope to make our universe, but there is some hope to make a very tiny little universe. This wouldn't be an expanding universe or anything. It would be a tiny little thing, some matter object that is governed by Einstein's equations. And just to give an idea of what this number is this number is comparable to the number of qubits that a quantum computer would need to break the classical communication codes. So you read in the newspapers that anytime soon now, quantum computers might break the classical communication codes. If you can build one that does that, it can also do this. So I'm personally more interested in this than in the communication codes, but now some people think that it won't happen anytime soon, but well, we'll see. It probably will happen in 30 years. Now in the future, what do we expect in the future? So hopefully all these type of developments will lead to a better understanding of the singularity inside black holes. And then this will translate, hopefully, to an understanding in cosmology of what happened with the beginning of the Big Bang. So usually, black holes are objects which are a little simpler to understand than cosmology. And in the past, some things were understood for black holes first, like Hawking radiation. And then the same type of phenomenon was then used to describe some aspects of cosmology. And hopefully, we can do the same thing with to describe the beginning of the Big Bang. And I think with that, I finish. Thank you. Thanks. Sure.
Okay, we can have a few questions. Somebody?
Hello. Hi,
Yeah.
Professor Maldacena. It's an honor to listen to your lecture. So my question is sort of broad. I just wanted to ask, what do you think in the next 10, 20 years is the biggest question in theoretical physics?
Well, that's very broad. There are many questions in theoretical physics. I describe one narrow aspect of theoretical
that
physics.
string theorists would like to answer.
Well, I think the biggest question we like to answer is what happened in the beginning of the Big Bang. That's the biggest question, and that's the main motivation for studying our field. That's what we really want to answer. Now, sometimes in science and physics, you cannot answer the question you really would like to answer. I would rather be speaking about the beginning of the Big Bang and how we understood the beginning of the Big Bang than these properties of black holes and so on. But we sometimes have to go take some detours and understand some other systems that we think will eventually help us understand these bigger questions. But yeah, that's I think the biggest question.
Okay, more questions.
Talk. Thanks for the nice talk. So I have a question that how can we reverse the physics occurring around the singularity? Or you have said a lot about singularity, right? But and you also said that we can do that encryption thing.
Yeah.
So how do you think that we can reverse the physics occurring around a singularity?
Well, I'm not sure. Well, there is one aspect of your question is perhaps the following. So when we talked about the singularity of a black hole, is something that is in your future, right? Well, the Big Bang singularity is something that it is in our past. So in that sense, they are different. But we think that since the laws of physics are time reversal invariant, understanding one and the other should not be too different. That's one way to explain the answer to your question. But I feel perhaps your question was related to what I was saying about getting the information out of black holes.
No, suppose if we reverse the space-time symmetry of any system, so will the singularity be? Can we like recreate the physics around occurring around singularity?
Yes, if you have something that is time reversal invariant, there will be singularities in the future and singularities in the past. So for example, the full black hole geometry has both a singularity in the future and the past. Now, I'm not sure if this is the answer to the question you want, or let me see. In what I discussed about reversing the formation of a black hole, we started with something that didn't have a black hole, formed the black hole. If you had complete access to the qubits that describe the system, you could, in principle, reverse that evolution and get the information back out. Now, that is difficult to do in practice. So I'm not sure if this is what your question refers to.
Maybe we can move on.
Okay, okay, thanks.
There are questions there.
Hi, Professor Maldacena. Thanks for a very great talk. I understand that you gave this talk, you were trying to explain a lot of things without the use of mathematics, and you gave analogies, and that might lead to some loopholes in understanding. Keeping that in mind, can you explain a bit more about or elaborate a bit more about the entangled black holes that you talked about? And would there be any consequences if these two black holes merge with each other? And would there be any physical differences between them merging and non-entangled black holes merging?
Okay, the first point I have to say is that if you find two black holes in nature, they are not going to be entangled in this way. So the state when they're entangled is a very special state that would be hard to make. Okay, so it's a, if you wish, it's a curiosity that displays a funny feature of spacetime, but it's not something that we expect we're going to find in the wild, let's say. So when you see these pictures of black holes merging, their two interiors are not connected. Now, you can still ask your question. So if you somehow manage to make this state and you now let them collide, what exactly will happen? So what will happen is you will form a bigger black hole, and any connection they had will be behind the horizon of that bigger black hole.
Okay, maybe one. Okay, maybe two more questions.
Thank you so much for the amazing talk, Professor. Relying on your analogy a little bit, I'm sorry if I misunderstood, but you spoke about qubits being on the surface of a hologram of sorts. Or like you made an analogy with water where the correlations existed below the surface, but all the events we observe are on the surface. So is there any way for particles on top of the surface to broach the surface or go to this faraway place where gravity exists? Is that possible at all?
Right. So if we are talking about the particles that live on the surface, they always live on the surface. So the idea is that the particles that live on the bulk they arise from correlations and properties of the particles that live on the surface. Now, I think what you're asking me is, if you have a particle that lives in the interior, can it approach this boundary? And the answer is yes. So what that means is that, for example, if you have some object that has some size, or there you have some correlations among particles, let's say with a given distance scale, it will correspond to some particle in the interior. Now you shrink that, if you somehow manage to shrink all those particles on the boundary, then the particle in the interior can approach the boundary. So the answer is yes, the particles in the interior can approach the boundary, if that's what you were asking.
Good evening, sir. My question is I'm curious about, like in LHC, like Large Hydrogen Collider, all elementary particles are we collide and the new particles generated. So same way, like in any possibility, like two black hole collide with each other. So what the next thing will happen? So is there anything chances? Like new
Okay,
galaxies and all the forms after colliding.
Yes. I don't know what the spirit of your question is. So if two black holes collide,
Yes.
they will form a bigger black holes. They will emit gravity waves, and we see that in the experiments. That's what happens with black holes. Now you could ask, could two black holes collide and make, I don't know, 10 little black holes or 10 smaller black holes? Well, that cannot happen according to general relativity.
Okay.
Now, in principle, it could happen in quantum general relativity, but it would be very, very suppressed for big black holes like the ones we observe through the experiments I mentioned. So that when you have black holes which are smaller and smaller and smaller, they behave more and more like particles. But yeah, bigger black holes cannot split into smaller ones.
Because black hole have like high gravitational field, so that's like it attract everything. So it's also attract this other black hole also.
I didn't understand the second question.
My question is like, sir, gravity, like black hole have high gravitational field, exactly. So it can attract another black hole.
Oh yes. So black holes are attracted to each other.
Yes.
Right. So so. I mean, I showed the picture of gravity waves that had two dots. So the idea is that you have two black holes that are attracted to each other, but they start with some velocities not radially directed, so they are orbiting each other, but they lose energy due to the emission of gravity waves. So they start approaching each other more and more and more until they eventually merge. And that whole process gives a certain pattern of gravity waves, which we can now detect here on the surface of the Earth and compare to the predictions that we get from this picture. And they agree.
Thank you, sir.
Okay, maybe we can stop here. So let's thank Juan again for a fantastic talk.
Please join us for high tea in the cafeteria. And there is a bus service arranged for the people who have come from outside, which will drop you off at Churchgate and CST. Just outside the wooden gate, HBA wooden gate.